last presentation is mine. For those who don't know me, my name is Ragab, and I work for Center for Ecology and Hydrology in Wallingford over the last 30 years. The title I selected for that talk is really Science, Technology, and Innovation, Moving with Time, and if possible, ahead of time. And I will just take you to a journey where we started in hydrology in particular, with measurements examples. The first example is the evaporation. When we started by evaporation, we started by Class A pan, and that was the first start to estimate the evaporation. And that, of course, doesn't take into account the biological resistance of the plants. So it has been overestimating the evaporation. Then we moved on to another technology, the ecovariance, what you see here on your left side, and then which is a reasonable scale, not big enough. Then we went to use centilometers, which a bigger scale, and centilometers comes in between the satellite scale or the remote sensing scale and the point scale. If you like, sometimes we call it the mesoscale. So the centilometers comes in between these two scales. So what the centilometer does is that we send actually a radio wave from transmitter or infrared as well, and we have a receiver at 5 to 10 kilometers distance. And due to the evaporation, the density of the air changes. And from that, we can actually calculate the actual evaporation, not the potential. And we have been applying that in Crete, we have been applying that in the UK, we have been applying that also in Napoli in Italy, and Bologna in Italy. From that measurements of centilometers, we can actually have a footprint of the centilometer, and we can split the total evaporation of a mixed crop field. How much comes from wheat, how much comes from maize, how much comes from tomato. And then you can actually also adjust your crop water requirements based on that split of the total actual evaporation measured by centilometers. When we looked at the values obtained by this new technology, centilometers, we plotted that against the ET node, or reference evapotranspiration as you call it, which is the gray continuous line. That's the ET node. And then we have the red and the blue dots, which the ecovariance actual evaporation measurements, while the orange dots there, it is the ET node multiplied by the crop coefficient, and as it's called crop evapotranspiration. And here you can see the centilometer and the ecovariance is giving us a lower values of actual evapotranspiration compared to what you calculate from Penman-Monteith's FAO modified version as ET node, and you multiply by the KC, that's what you get here. So the ratio of actual evaporation measured by the new technology was actually half of what they actually estimate from the FAO Penman-Monteith equation. That can give you saving of water almost more than 50% if you add your irrigation amount based on actual evaporation, not as a potential evapotranspiration. So that's a new piece of technology that's useful. And once again, centilometer falls between the point scale and the remote sensing scale, which is the mesoscale. Now, the evaporation, of course, as the first two speakers, Jack and John, refer to the evapotranspiration from remote sensing, so that's the scale above the centilometry. Now, the second issue is the soil moisture. We have been battling with soil moisture for decades, and I have been in that journey, and also my colleague here, Professor Finn Plauborg from Aarhus University, who was also with me in that journey, battling with the measurements of soil moisture over so many projects and over so many years. And we started by taking soil cores. And here the soil cores on the top left, And after that, we went to neutron probe, and we were told it is radioactive source and it's still a point measurement anyway. So we got a non-radioactive source, and that's here the, if I can get the pointer working. The delta T probe. The pointer is not really sharp enough, but this is the delta T probe where it works like neutron probe. It works exactly like neutron probe. You measure soil moisture at depth. It is a point measurement, but less radioactive source included. Then it is also a point measurement. Heterogeneity is not really dealt with. Then we went to something else, that ART, or the Electro Resistivity Tomography, when we use actually transect, and we measure soil moisture on transect. Each transect 32 meters, and sometimes in the field we do 64 meters using the battery of the Land Rover. As you see here, that's what we do in the field. And also this has been used for irrigation, like center pivot or drip irrigation, to look at heterogeneity or homogeneity of water application. So that became a new technology developed by a geophysicist, and we started to use it as a hydrologist and irrigation also practitioners. And from there, we can also see the change in the soil moisture content under different vegetation cover. And we can also see that profile. We had in 2006 drought period in the UK. And we have been monitoring the soil moisture over time to see really how the soil moisture and the survival of vegetation level under the drought conditions. Then we went further to a different scale, a larger scale, Cosmos. Cosmos is another way to measure soil moisture for an area based with a radius 300 to 700 meters. And the Cosmos technology actually is using the natural Cosmos rays that comes from the stratosphere, and then produces neutron when it interacts with the geosphere. And those neutrons, they have the same atomic weight of the hydrogen of the water. So when they hit the hydrogen of the water, they slow down in velocity, and we count the velocity of slowed down neutrons as indicator of soil moisture content. So we have been using that and in a project, Water for Crops. And here you can see actually the top there is the soil moisture, and you can see the reaction to the rainfall or irrigation. It's very sensitive, it reacts very quick to any addition of water to the soil. And also we managed here to calculate the soil moisture deficit as indication for how much water you need to apply using the Cosmos. And also we have been giving it color-coded values that was arranged based on FAO. When it's green here in the lower plot, you don't need to irrigate, there is no stress. When it goes to yellow, it's just very light stress. Amber, it means a medium stress level. Red, you must irrigate because it is really a highly stressed crop. Then the Cosmos went into a different technology level, which is now goes into that like beach buggy, where you can drive around and you can make your contour lines of the soil moisture. And that's now the latest technology in Cosmos. And once again, that falls between the point and the remote sensing scale. So that fills the gap between these two as a mesoscale. And that's the next scale up, of course, as John Bolton mentioned about the soil moisture mapping using the remote sensing. The other thing for technology, how we move with technology, getting the water to the field. If you look at the temples here in Egypt, you will see this is how the farmers started to get the water from the canal to the field. And then it moved into tambour. And that's another technology a bit further ahead. And then they moved into a water wheel. Sometimes they tried themselves to turn it. It became too difficult to the farmers. They used their livestock to turn the wheel and to get the water to the field. And then the technology went on and we got the pumps. And diesel pumps, and now of course you have electric pumps, and now we have also the the solar energy powered pumps. Then we came to the efficiency of water. And at the reservoir level, we find most of the time we lose about 1/3 of water in reservoirs. So some clever thinking after that came with the technology of floating solar panels, floating on the water to reduce the evaporation from the reservoirs, and at the same time produces energy that the farmers can use for dairy products to produce ice cream, butter, and so on. So the technology has been really moving from the shadoof, tambour, to that sort of things, really. And then we came to sugarcane. And sugarcane, this is a sugarcane field with furrow irrigation, and we introduced the drip irrigation on Mauritius island, and you can see there is a big difference between the two, the furrow and the drip. The drip produced more yield than the furrow for sugarcane. And then we came to another idea with drip irrigation. What about irrigating half of the root zone by using subsurface drip irrigation? So we applied that in 2 projects with Saphir, and also applied that in Water for Crops project funded by European Commission. And here we apply we have twin drip lines. We irrigate half of the root zone once a time. And we alternate the 2 systems. So at once you only irrigate half of the vertical root zone and you alternate. And then you can produce some good crops like potatoes and tomatoes. We started to do that in so many countries. It has been successful. And it actually saves 26% of the water used under the normal drip irrigation, and it saves 46% compared to the sprinkler irrigation. And we started also to apply the solar energy in center pivot, and we could actually save more than 30% of the water and energy when we use a solar-powered center pivot with low nozzles close to the surface, which is actually also a new technology that would allow less losses by evaporation or by wind drift. At the same time, if we are using saline water or treated wastewater, it is better to use a low-level nozzles closer to the ground than high nozzles at the same time. Then we use the solar energy to pump water out of the ground instead of the shadoof and other things. And then we started to use sensors to trigger the irrigation when we have an idea about what happens with the soil moisture. So we have sensors here under the plants that they can measure the soil moisture, and then they give a signal to be transmitted to a server, and the server talks to the control panel that would trigger irrigation, and stops when the soil moisture measured by the sensor to say, I have got enough in the root zone. And then we moved to precision farming. Laser came into our technology, and we have been also improving the efficiency of the irrigation systems. And here you have all the tractors nowadays. They are now full of gadgets and devices than before. And we are now using also drones, and those drones, they actually estimate the irrigation, and I have seen that in Toulouse in France for several years, where they use that technology. And also we are using it for nitrogen deficiency indicator, and also it has been used in Australia in different applications to look at the water resources and leakage and all the water supply network. And also it monitors the water quality at the same time in lakes and reservoirs. Another biotechnology came around, and in one of the projects that I've been working with in Water for Crops, we managed to get a maize grows in Canada completely in 2 months. And the University of Bologna, they have been taking that variety, and they have been trying to have a hybrid between the local maize and the Canadian maize to reduce the season of corn that grows in Italy. And getting the season shorter, it means you save also irrigation water. And also we try to simplify our science output. So all of us will get results, and these results will get promoted by, and some results, of course, it gives you a good CV, but at the same time, the end user of us are someone else. And that someone else might not be able to understand and digest the language we use in our scientific publications. So we have to put that actually results into a simple way, and a simple way is apps. And if you find all the common thing in that picture, all those farmers all over the world, they have one thing in common. They have all of them mobiles. And therefore, we have been, so far in the UK, we have produced about 7 apps for farmers. And those 7 apps, the farmer can use the app and while in the field. Don't expect farmer to take a laptop to the field. And don't expect the farmer to take a desktop to the field. But you do expect farmer to have a mobile in the field. And I think this is the technology we should really move to by taking our scientific results, academic results, and put it in simple, plain language for the locals in a mobile app. We have so many switches really to use to improve our knowledge and also to be innovative. And I have seen yesterday STEM stand here outside, and this actually group are secondary school group, and to me they are really the leaders of innovations at that young age. It's really I have seen desalination innovation. I have seen a grey water use at low cost. I have seen also precision irrigation shown by very young, talented, very promising, young, innovative leaders of the future. With that, really, I thank you for attending the session.